how we were analyzing the gradient descent, then we will move back to stochastic gradient descent. So the main point that you should remember is like, we don't necessarily know these algorithms converging to the right spot we want them to converge. So either you develop empirical techniques, or if your function is nice enough, you try to prove it mathematically. And then the things you prove mathematically serves you as an intuition or like an inspiration for the stuff you would do with functions that you're not necessarily able to handle rigorously in a mathy way. But you keep that intuition in mind, you try to make it happen empirically, basically. For example, you started your training, things are going well, like you see the decrease in your cost function. And then all of a sudden, like it starts, even increasing sometime. What do you see empirically? Your learning rate is so high, it's jumping around. So you reduce down the learning rate. Do you know necessarily this is the best thing to do? No. You're trying to imitate what would happen in the stuff we will mathematically see now, right? Or you start your training, usually don't keep your learning rate very small in the beginning because there is hopefully room for improvement. It jumps a little bit, and then it starts slowly decreasing afterward. So we try to imitate what we can do mathematically by our practical trick, basically. Okay. So that's why I'm trying to show you how things are derived. So this is the analysis of gradient descent for a nicest function we could imagine. It's convex and L smooth. And in that case, we could even fix the learning rate to 1 over L. And then we were trying to analyze how does things go. And the main punchline is going to be, if you do T iterations, the difference from your spot minus the best, this is the minimum. This is the smallest you could achieve. This is what you're trying to find, right? By the way, all optimization stuff is a search algorithm, right? If I even know this, I don't need to do any iteration. I could just fly there and then say, this is the best. But the point is, we don't know, we are searching, right? It's a search. All optimization is a search algorithm. Okay. And then, so the guarantee you could prove is like the place you started your iteration with, distance to the optimal spot, divided by the number of steps times 2 multiplied with that L in that function properties. So at the end, this is what you got. You go T steps, you divide the error by T. Okay? So then if you have an idea about how far off you might be when you start, and if you want to make this error less than a threshold, then you have an idea how many iterations you need to go for. Okay? That's the case where things are super nice. And why in that case we are able to prove this, that in other cases we are not able to prove? Because we got two things. As soon as it's smooth, we got this decrease guarantee. I iterate one, and I got at least minus 2 over L times how big was the gradient much descent decrease in my value. So at every step, I'm doing something. That's first. It's because the function is nice, smooth, right? Second one, since it is convex, I also know the convex kind of stays above the gradient. And I could also utilize it when I try to understand what gradient descent does to my algorithm function, right? And this is the second thing. Take anything you like, put any y, fy will be bigger than fxk, y minus xk times the gradient, right? And I plug in this optimal thing just for analysis to go nice. And so you combine these two, you get the first thing out of it. That means fxk plus 1 is less than this thing minus that, right? And for this, I could get an inequality from here. What is fxk? It's less than this guy minus this stuff, right? So you just plug it in right there, then you got your fxk plus 1 is less than the optimal thing plus this. When you go to the other side, it switches sign. It becomes xk minus x squared. It's right here. And then this stuff right there is sitting right there. I basically plug in the second thing into the first. Then I have this guarantee now. I have this type of decrease, but it looks a little unwieldy to handle. So you do some algebra. And the algebra, when you do it, it tells you, just look at here, it says this stuff here that you see looks a bit unwieldy. is actually equal to something much nicer. Okay, this is straightforward algebra. Okay, you need to go through it, but there's no magic. That's what I'm trying to say. The unwieldy stuff that came out that apparently can be written as I iterated xk plus 1, the distance squared, minus xk squared, multiplied with L over 2 is literally the thing you got right there. When you plug in this to that estimate, it starts looking much nicer. It will look like this. fxk is less than or equal to optimal plus this quantity. Okay? This is where I am at the kth iteration, 5th and 100th, whatever that k may be. Okay? Now let's say I go like 1,000 steps. And at every step, I know this inequality. Can I kind of accumulate them and see where I am at the end? Okay, what I will do, I'll write this inequality for every step and then try to sum them up, okay? So this is the entire sum from beginning till end. And I know this difference is decreasing. I'm always making it better and better. So the end result is the smallest in this sum, right? Okay, the entire sum is less than sum up all that stuff. And now divided by the number of steps, left and right. Left, you got this sum divided by number of steps. And on the right, you got this thing divided by number of steps. And the nice thing is when you sum them up, they start canceling each other. That's why this thing works out. Because you see, like you say x10 minus blah minus x9. And in the next step, it becomes x11 minus x10. So it keeps canceling each other. You only end up getting the very last thing remaining, and you're dividing it with the number of steps. On the left, you got kind of average over all the differences. But we know the smallest difference is the latest one. For sure, it's less than this average. This is all I care about. And I know this average is bigger than that because this is the smallest one. Okay? So that means this is for sure is less than this. And as you see, potentially you can prove even more sometimes. I'm doing a lot of loose stat, right? I'm taking average, saying less than that. Maybe it's not. Maybe it is much less than the average. Okay? But even in this way, we are able to prove for convex a very legitimate guarantee. Okay? And that's kind of what people imitate when they try to design stochastic gradient descent. Before I go, any questions about this? You don't have to reproduce the proof on top of your head, but I hope at least the idea was not so hard to follow. Just to repeat it once again, all I did was like write the definitions coming off of, this is called descent lemma for any function that is smooth. This is for convex. You combine that, then you do some algebra. It starts looking much nicer. And you got this thing right here. And you sum it up, it starts canceling out. And when it cancels out, you would get only the last one and the sum, and then you divide it by number of steps. And you realize the entire sum divided by number of steps is bigger than the smallest one for sure. This is like average of the sum. And then the smallest one is what you're trying to handle anyway. Okay. Any questions about this? Okay. As I said, if you did not follow every single line, that's okay. But I hope you're seeing it's not terribly complicated, okay? I know you see a lot of math here, but it's not like a very high technology creation. Just literally go line by line, check what you can prove. Okay, now let me go back to stochastic gradient descent discussion. So before we start anything, this is, suppose, your loss function. Your data, your label, check it against total loss. And the gradient of this is this guy. Right? And suppose yesterday, probably it was John, he's not here yet, was asking me like, if I have an application that I would like to be very certain of my gradient, and can I just do it all? Well, that depends on your computational resources and the time you have. Why? If you want to compute this explicitly, it will involve every single data point. Okay, what does that mean? Let's say I'm training a neural net. I am doing an update only after I went through every data I got. That's what would that mean. Okay, because you're trying to compute the loss and the gradient using every single data point you got in this way. Right? That's usually not what you would like to do. You would like to use some of your data, change your parameters, use some other, change more, and eventually hope you will arrive somewhere reasonable. So the entire reason for the invention of stochastic gradient descent is this, just for speed purposes. It's not for mathy purposes, okay? So later people also figured it's maybe also helpful mathematically because it introduces some randomness. Randomness seems to regularize the landscape. It kind of makes you escape from very pathological cases you could fall in. There is also some slight benefits, turns out. But initially, the entire reason is like, I want to compute something. It's too much data to handle. What do I do? Well, one case is you can push it to extreme. You can update after every single data point. Okay? Take one data, update. Take other data, update. And this is called online algorithms. It's streaming, basically. You don't save any data. It comes in, like streaming your Netflix. Yeah. So it comes in, your thing updates, forgets. Comes in, updates. That's the most extreme case. The other extreme is put all the data in, then update. Usually you want to be somewhere in between. Okay? So that's called mini batching. So we will pick a batch of data in a random way and keep updating. And more conceptually, what we would like to do is like we would like to design a random function that flips a coin. This theta is the random thing here. And it creates something that is cheap to compute. And then in expectation, it should still match what I would like to do in an ideal hypothetical world. Okay? And an amazing thing is you end up proving mathematically, even this is only matching in expectation, you still can get some guarantees for algorithm convergence. That's the interesting part. So I'll give you some examples we have done last time. I'll go through quickly again. But as soon as you got this function, you replace the gradient with this cheat thing and keep iterating, just like gradient descent. That's the only difference from stochastic or usual gradient descent. The gradient is created in a stochastic way. Okay. So I got another question last time, which was about every time this algorithm is tossing a coin or doing something random, are they related to each other? In the standard stochastic gradient descent, at every step you use an independent randomness. Okay. That's the standard default version. Oh, it can make sense not to repeat the same data you might have seen it before, right? So if I got like a million data points, I'm putting them into 50 data point small chunks, and I just sample one of those chunks. I train my thing through. If I sample again, if I'm going to the same chunk, probably that's not a great idea. I want to kind of diversify. So that is also possible. This is a little trickier to analyze and a little harder to do, but not too hard. Basically, the difference is sampling or sampling without replacement. Sampling allows you to pick whatever you can repeat. Sampling without replacement means you're not sampling again what you sampled before. This means you will go through all your data, then you'll reset and start counting. And that version is usually called random deshuffling. I don't know why they call it. So that's just stochastic gradient descent without replacement. But if in literature, they would call it random deshuffling. Okay? And there are papers saying random deshuffling beats stochastic gradient descent. Beats it by that or whatever. So there's the evidence this is not a bad. All right, let's get going. So far, I hope the ideas of gradient descent make sense. Population is and again, create something random that's deep, but correctly. So, an example of function is something like this linear I made that. Second example, doesn't make sense. Why is it randomly simulating? I create from normal data. I have made something only one of them is setting it against the and maybe so that step here is what it should be in the ideal. You need to compute expectation. How would you yeah, based on and expectation of what would you this right? So the value has no rapture. That makes probably the first and in you get to cover every single day. I mean, it looks like this mechanism. I forgot to them. Ratings, and then you use this guy in like improve SM. So that's the end of the grading. And this in the mean, for example, now if you send like think about that. If you're using this random yeah, how do you be sure that really reasonable? So, scared of all this you can do this thing. Yeah, different that same thing. And this time is not to cheap. It's I'm sick. Is the shower. Yeah. It's first point. But yeah, example. Expectation. Then carefully realize actually on the thing but they will only use this to the next day. You only have some TV. You can't last expectation become education. Education is that's all we do. Expectation be planning. Oh, and no expectation. That could be something. Something random. Yes, there's something always deviation. We talk about that deviation, but it doesn't mean that exactly from this point. The next thing is that you can also go into a long region. Take from that. That's all that we do. And life. These are very important. Okay. So in my class, just the result. Basically, is the method for expectation and start working for so it was Like, for this canvas, if you look at line energy, I've introduced applications of this gradient descent idea, which ends up in the end of the it's gradient descent and Python's problem. And turns out it's reducible and the paying name for also is called this is like a loss. And okay, stuff in content makes practice. You so stability is question and how you get to the Polish person that is nothing. It's trying to the same people. And people that rest of the people that give me and it's all something nice such that they have linear system. If this and are not the same thing, either is not whole. Or you take about it's to be like you experience life is a expect of the it's maybe it doesn't all I thought I'm easy. So when you define more of this and brilliant stuff, like this, if you have algorithms, how would you decide for the like you can set the base you could use the algorithm because the first input that algorithm or first that for writing or B because this is a measure in let's say the matrix match it's all the different and there's also before we found it. That's the thing. No, it's about the latest matrix. You know, the latest matrix. One thing is called my is pretty embedded. It's not solve everything. Then looks like the lens. I just it's small. And you also write down the thing that's looking regulation. So I make it is a role on the that multiplies it. Or you want to essentially so first of all, the best you choose to be okay, and then it's only up to the people. I'm your audience not made that right. Now you see that optimization normalization, you need to know how gradient is coming out. This is what and go by age categories. Once most people will be careful as it said that the computing ratings like that will be and then keep doing it. The only thing for example that you need to pay the lowest random selection. The reason being the first law, the vector was huge. Suppose the second one very small. The paragraph equals small. That multiply the small letter the small number. So taking that other things from that one attacking every also that only gains. So I think the prioritized randomly to zero. And that's what they do. It's a whole thing. Theta came from the the point. I'll figure out probability for theta being a number that is using zero equals to normal rho divided by the summation of all numbers of rows. Okay. This guy had a bit norm. Let me put more probability. That's how you define a randomly. Uh, I think expectation that it's almost a but but usually that somebody has to do the right. It's pretty simple. Implement. But the hard to only the two it doesn't make it. When open nice the math camera. Okay. In this case, math uh, I might say but you know, in my head, I would like to go through the math entirely. It's very beautiful. But I know the teacher it so implies you realize shows up in all kinds of places. It's going to go on even when you compute anything but basically maybe I believe this like you need to see the and then what is it? You think because of your making something that you they think about you find out you know, very much and and I'm kind of popping up but brain was working and the other but in terms of that you actually really got to but very of the level and banks all the exist. Seeing something in the direction of average. And again, this one can show how is the big number. If you call it yield condition, the same. You so accuracy. If it's small, then you're like, okay, this is nice. And if it's big, you know, sometimes I could change the matrix to something else. Solve it for this new matrix. You should have a way of transforming that function. Okay. That's called triple D. I'm just You change your problem to something totally different. That's what you're trying to guess. And you plan to make something, and it becomes a doing. You so different, and you kind of stay back to home. Because it looks like it. But it looks like I checked the crowd for it, but there is still people. But that's not. I think it's unbelievable. The problem is, and but overall, this thing turns out you can analyze this randomized algorithm that will be not. If you're not able to doing this due to learning and even I want to say, not sure. So let's say the extension of the system value, yeah, value add. Say take one minus the completed number. So one minus number. So this is maybe look at this accurate. This is a small number. How very how quickly that is huge number only cost of $1. But this number is huge. Well, we might as well that is going to be stay or as long as something goes forward and not it's gonna be fine. And second thing for start uh I believe that is actually hard. Probably I shouldn't do it for the sake of time. But maybe do that and the rest you can open up to it. It goes like I take one that I multiply by matrix, like something like that. It's really what in taking effect in A and looking at the output and say what is the smallest thing I can get out of it? That's the thing, the smallest thing. Smallest thing around is that's the smallest thing. It's like yeah. And I'm not kidding. Even some of the goals actually looking at convenience for too long. So you can both sides. Here you have all of this. The right hand side, you still get the image of original things here. Right. What is the evil? What is the quantity? If will be of non realize so even if I don't use all these just to be the back to the department entire will keep up university. That's how the expected behavior of risk and something mapping and This is to show overall thing. Everybody tries this one. Means that people are the fear like I decided to people to be proportional to how they know. The role is a huge part player. The role is a small number because be careful, be patient to your mind. And you need to finish making that space. And maybe do that to like, in your back. And the back now, uh, any questions over the body will get there. Not here. It's I feel you get off and be motivated as good even talking about particularly so and like that's kind of what it is. Process about because in that now now that we the team in technical relations a few of the past slogan checks that we using maybe into so you don't think and keep out of this. So they're not but to be able to show you those and the idea behind those is you can just boost your unless your problem was that's linear is so it proves something about and but you're not necessarily trying to do things that you get it. So how about this is and the mistake later based on the second but then we do it. So if you really want to be sure that we're optimizing up, you can do anything. Let's see, thinking about something that's not exactly what you want to be. You have to do it smarter. Usually that season. But I'll get all that activity up to you. That purely that's something in the me. It the matrix here. What's the choice to makes people? This is a direction you're trying to do. You I'm sort of certain it all that or else you find the mix community to be that relation. Now let me show you the versions of and then over so here I don't quickly without this now that should be for a delta not feel so so let's in so the idea here is I'll try to accumulate all the greatness I have seen and make that was remember the action from really great that we update this event matrix and taking away taking its past making it up into the a matrix and doing this every step of my grade. So in that step you can matrix and all these things learning you're not your gradient matrix to be able to change any that this people last time I forget about novelty I realized this is actually the design but in the same even there the universe will be small and this means and actually that look at all the universe will go on of these so handle anything more and more as you can know yeah at the end small matrix you have to like I just and I have to learn more about the earth but I think intuition right and I should do smaller right how small how maximum without the controls that accumulate accumulate maintenance. Okay. And there's some practical ways say sometimes like they say I'm not going to use the entire use but use without the different engagements the target actually will be below how the trades that some being I'll show you more of those variations. This is this came out in my consolidation period. So which means they were working with state data and they have to run state concept for like okay. In this the way you copy that stuff, really extent this one okay stuff. Going to have like radiance there. You have to prove the email out. And then not they prove it. Okay. That's why it is. Even though it's so that each at the building that's special. Nothing nothing about in brain. You would say some the from the stuff and what it makes said to think or to make if it's it box it's about a box it will have that even this so you have what and you start doing that you do your team it's that's what you number but the thing is like the matrix the user and they and just this is the is how that's not you I use actually needs to be a small gate. So the very my patient you have the gate then not I'll get it. I see a number and a third divided by another number. I would know this correct matrix and dividing instantly. This is the type of data description about the image method for me. You could always I'll still not offer to fund. And the coefficient involved, I don't think so if you regularize thing usually regular feast times one. That's it. The rate is back. As the zero each of random meters and uh, you need it. So they also the option for learning based the mathematics is the learning rate. If you want to check the hearing excellent. If I get the is up to power incorrect. I be able to go forward. It is very fresh. No problem. It is happening. It's the problem. It is only 2 meters that step. It's like the whole that start raising people and just like then prioritizing the and then rich decay. You get to massive decay as well. If you say, let me show you how it goes. This is what I can make a and just in the very last step, and the one I said it. If they details help, you're putting how that thing and how affecting other people. And you think how to check that's like the second step that's then we not that. As you the first like smaller future to how I do them. Simple nothing you can change it along with. That's and it was still easier so that you see it's accumulate very points that will be second yes they about want to go everything and go and that's yeah like so it's about actually innovating and asking me and here's the thing he said no It's about using machine learning. And what is actually like change the gradient. What's the gradient in function? And it's like look like I would be like so change in my thinking, like change in my brain. At least I'll next year. Learning will be doing it. This in the scale of learning. Anything just to like change it. How empathy we have by the data to get peaceful they do not see that and to break it. Second part, and one running that's going to be very basic I did not need it. It's something each bird go so we're trying to so we see the creative they go to the okay, let's give me a second to show you that is. There's the main thing right there. And so, yeah, it's just see this camera, right? You get one if you want to imitate version, credit, or also message. Like, previous ones, they basically have this is the latest ever dream. It's not here in there. Okay. And you, I'm sorry. Yeah. And the other case here, they do like, yes, so, uh, yes, like in of trading, like a bit of and you create up to create action and you achieve to feel and I think he and the advantage is the very the amount to decay gradient and the amount to decay change is the same number. And this is the number because now if you have there's something else there. So they will that decay is not decay. That decay and the regular decay. That's what that's. Usually, I'll think that problem maybe whatever and they go back to right there. All of these that we were confident is trying to do what I do them and trying to care. And I don't know the trying to do that way right a little bit. So maybe you can probably okay come up with a way that tries to imitate action, but still more efficient than the runtime efficient that people have on. It's not like and so this is a and there's any popular possibility in that way people appreciate right and it is preference and they did not what they're doing they're trying to do that's something do that's the but in do reason so here the idea like India, you have to take care of you you're learning here you see the you see working by it you will see the solar and that you could actually even if they focus and also I always tell you what that is nice because there's more before there's the bad that else so finding show you that I'll be able to yeah really in that discussion we got some called text the exploration of the manager is before start and in your thoughts and any questions from our female that up to mind. And now we can just to say like that. So that's pretty hard. So the main thing the stuff applies in terms of about the you could learn the tech because you found that even a bad session that people if you are in so much it's usually why to do this if you can't it would be very for training it's really okay because it's not or the only thing that you need like if you're still big then that you need so usually I don't one more it's really called isolate. It's called act learning. Start talking about the daily research. Your years, but not your more. You don't want to, you don't go to okay. But your business doesn't match that. So at the end of this, look, go and build this global. Holiness can be bold, also called great at the moment. Let me give some moment in the direction I am thinking like my great is that now that I that would be that practical give more impact. That's very important. It's like that. It's and that are is not like they would have moments almost everything. So I always like it is like the scene of the moment. I allow me in the percent. That's how we started. And if you catch at the moment, you'll already heard. No, moment doesn't worry. Here's the example. So I'm sorry. So they have things like it comes up like that's better something on active they have they run one message and it seems like it does something relatively it's like even if you gave them one look still not over and they more like turns out it's all like it was they back they recycling the cross. It's not like he probably other things he did before he got here. But somebody moment that can keep working. And he wrote on this. But the thing about this was in community information every day. So they're always thinking now that's is what is organization doing stuff. They go to like but yeah so momentum the direction. So at the point I see really before the next year. So I look at I'm going to push right now. And what that's actually well maybe first computer great engineers first being ready. And so it goes like okay, said okay. I really think about it. And that's really research. People also made it in that portion be back in the next. Yes, I mean, this actually I think so much. I can comment that. In fact, it's also in this from on the question. Uh, now I mean by optimal, this is your approach. Famous people pattern for called like environment. And you don't have to interact in our value. So it look at all the how to do it. But the best you do is running the thing. It shows this is the best. If you allow me to ask, you think that's whatever I would say what's the like I created what you want to check out the person. It's your action. If you took two that is what it is. I choose either okay. So you do you do they say this is it proves exploited methods that's not actually impacting faithful uploading stable. Because that's the most family, he actually has a trade offer. It's not the only thing that actually brings that from the teacher of my teacher. And talking about that, some people. So now, the thing, it's the temple. That's the yes, that's the Missy, it's like, yeah, the people that like we not know about the explanation to the it's definition. People then started the internet somewhere excellent. Like, so all my like what is excellent? But it's what is really my mind. Because we know more now. Still don't know enough. That's me. So, eight, I got the exploration. What do you how can we systematically accelerate all kinds of long term? Right. And like the other. And if we need to make it look at it, so so I and from people, you know, I should be let's say for the yes, I clap my house move away. It's me, people on it's I they say, let me stuff and This is not because I do for hundreds of seniors if we release that. This is a way to so now, right? That's yeah. It's from there they to this. They understand. So and energy you're not all of these people able I think that's energy this something called if the short of and then talking about like going and then else so 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 if you do this more action and it's great like what yeah you complete this just say the moment you think that then you have to you feel the great this is the plot is a record that you do and this is an 8-bit trick because it should be it's your one is it and you're not the number sure so you know they okay also we you don't think that's the difference is that it's that you want in all the you're right. It's a and let me show you all that. And then we start to ask around for a minute. Here's a very nice link. So it often like it's important. See how it goes. Also, that's much so that